Hello and welcome to Earthly Teachings. Today, we're diving into a crucial topic in Electrotechnics N4. We'll be discussing the losses that occur in transformers. While they might seem like a disadvantage, understanding them is key to appreciating why transformers are so efficient. By the end of this tutorial, First, you'll be able to define why transformers operate at high efficiency, even with losses. Second, you'll be able to name and classify the two main categories of losses. And third, you'll be able to describe each specific type of loss, including how they are caused and how they can be limited. So, let's get started and demystify transformer losses. First, let's address the big question. Why are transformers so efficient? In our study of ideal transformers, we learned that the power output equals the power input. In other words, an ideal transformer has 0 losses and 100% efficiency. The formula for efficiency, EI, is simply the output power divided by the input power, expressed as a percentage. For an ideal transformer, with 0 losses, the output power is equal to the input power, resulting in a perfect 100% efficiency. Of course, in the real world, no machine is perfect. All transformers experience some energy loss, which means their efficiency is always less than 100%. The energy input is not all converted to useful output. Some of it is dissipated as heat. However, transformers operate at a very high efficiency, often exceeding 95%. This remarkable efficiency is due to a key design feature. Transformers have no moving parts. This eliminates the two major types of mechanical energy losses found in rotating machinery like motors and generators. There are no bearings or commutators to cause frictional loss, and there is no armature or cooling fan battling air resistance to cause windage loss. Because these mechanical losses are absent, the efficiency of a transformer is limited only by its electrical and magnetic losses. And it is the absence of moving parts that allows transformers to be so incredibly efficient. Now that we understand why transformers are so efficient, let's look at where the losses do occur. We can classify transformer losses into two main categories. Let's bring up the diagram from our notes, which provides a great visual overview. As you can see, all transformer losses are divided into two main groups. On one side, we have variable losses, and on the other, constant losses. This is a fundamental distinction. Variable losses change with the amount of load on the transformer, while constant losses stay the same regardless of the load. We can think of this as variable losses depend on the output power delivered, while constant losses are present even when the transformer is just turned on and doing nothing. Under variable losses, we have copper losses and stray losses. Under constant losses, we find iron losses and dielectric losses. Iron losses are further subdivided into hysteresis loss and eddy current loss. We will now go through each of these losses one by one, explaining what causes them and how they are handled in transformer design. Let's begin with the first category, variable losses. As we said, these are losses that change depending on the load, which is the amount of electrical power the transformer is delivering to a circuit. We will first discuss copper losses. What are copper losses? They are simply the heat generated due to the electrical resistance of the windings. When current flows through any wire, some electrical energy is converted into heat. This heat is energy lost. These losses occur in both the primary and the secondary windings of the transformer. Because they are directly caused by the flow of current, we can express copper losses using the familiar power formula. This formula is power equals current squared times resistance. We can also refer to these as I squared R losses. They are variable because the amount of current flowing in the windings depends entirely on the load. More load means more current, and more current means higher copper losses. To minimize copper losses, transformer designers use windings made of materials with very low electrical resistance, like copper, and design the wire with a sufficient cross-sectional area to keep resistance low. The second type of variable loss is known as stray losses. Stray losses are also current-dependent, but they arise from a phenomenon called leakage flux. Leakage flux is the portion of the magnetic flux created by the primary winding that does not link with the secondary winding. Instead, this stray flux spreads out and cuts through other conductive parts of the transformer, like its support structure or tank. When this leakage flux cuts through conductive metal, it induces small circulating currents within those parts. These are called eddy currents. These unwanted eddy currents create I²R losses, just like in the windings, and dissipate energy as heat in the support structure. This heat is not useful for the transformer's operation. It's just wasted energy. Therefore, it's classified as a loss. Like copper losses, stray losses increase as the load and the corresponding currents increase. Transformers are designed to minimize leakage flux, but it can never be completely eliminated. Now let's move on to our second main category, constant losses. As the name suggests, these losses remain relatively fixed or constant regardless of the load on the transformer. The first and largest component of constant losses are iron losses. These are also known as core losses because they occur primarily in the transformer's iron core. Unlike copper losses, which are current dependent, iron losses are voltage dependent. They are present as long as the primary winding is connected to a voltage supply. Iron losses are caused by two phenomena: hysteresis loss and eddy current loss. Let's first explore hysteresis loss. This loss is fundamentally a magnetic phenomenon. To understand it, we must first understand hysteresis. Hysteresis refers to the lagging of the magnetic induction or flux behind the magnetizing force. Think of it like this. When the primary coil creates a magnetic field, it magnetizes the core. However, when the alternating current reverses and tries to demagnetize the core material has a memory and resists becoming demagnetized. It retains some residual magnetism. For the next half cycle of current, energy must be used to first overcome this residual magnetism and then magnetize the core in the opposite direction. Hysteresis loss is simply this energy that is wasted or lost as heat in the core material as it is repeatedly magnetized and demagnetized. To limit this loss, manufacturers use special core materials. For example, silicon steel is commonly used because it retains very little magnetism and requires less energy to reverse its magnetic state. The second type of iron loss is eddy current loss. This loss also occurs in the iron core. The alternating magnetic flux in the core induces an electromotive force, or EMF, right within the conductive iron core itself. Because the core is conductive, this EMF causes swirling currents to flow in loops similar to eddies in a stream. These are the eddy currents. Just like in the windings, these eddy currents encounter resistance in the core material, and as they flow, they generate heat. This heat is wasted energy, contributing to the transformer's losses. This seems problematic, but there's an ingenious solution: core lamination. Instead of using one solid piece of iron for the core, it is made up of thin, insulated sheets, or laminations. The insulation between these laminations is typically varnish or paper. By breaking up the solid core into many thin, insulated layers, the path length for the eddy currents is drastically increased, which in turn dramatically increases the resistance of that path. The higher resistance leads to much smaller eddy currents and thus significantly reduced heat generation and energy loss. The final constant loss we'll discuss is dielectric loss. Dielectric losses are unique because they don't occur in the windings or the core. They occur in the insulating materials of the transformer. Transformers contain solid insulation, like paper or mica, and often transformer oil. These materials are called dielectrics because they are very poor electrical conductors. Their job is to insulate the high-voltage windings from the low-voltage windings and from the transformer tank. Ideally, dielectrics would be perfect insulators with infinite resistance. In reality, they have a very, very high but finite resistance. When an alternating voltage is applied, a tiny leakage current can flow through the dielectric. This tiny current causes a minute amount of I²R heating in the insulation itself. This is the dielectric loss. Under normal operating conditions, these losses are extremely small, often negligible. However, dielectric losses become significant and problematic if the insulation is damaged or deteriorates due to age, heat, or moisture. This can lead to insulation breakdown and a transformer failure. Regular maintenance and oil testing are essential to prevent this. Now that we've covered all the types of losses, let's test our understanding with a short activity. These are the kinds of questions you might find in an Electrotechnics N4 assessment. Let's go through them one by one. We will now begin Activity 4.4. Question 1 asks why transformers operate at a high efficiency. We discussed this at the beginning of the video. The answer, worth 3 marks, is that transformers have no moving parts. This eliminates frictional and windage losses, which are major energy losses in other electrical machines. Question 2. Name the 2 categories of losses that occur in a transformer. Look at our main flowchart diagram. The 2 main categories are variable losses and constant losses. That's 1 mark for each. Let's continue with Activity 4.4, focusing on questions 3, 4, and 5. Question 3 asks us to state whether 2 statements are true or false. Part 3.1 states, variable losses are phase angle dependent. What do you think? Is this true or false? The answer is false. Variable losses, like copper losses, depend on the magnitude of the current, which is determined by the load. While the phase angle can affect the reactive power, the real power loss, I squared R, is about the current's magnitude. Part 3.2 asks, iron losses are current dependent. We spent some time on this. True or false? The answer is also false. Iron losses, which are constant losses, depend on the voltage, not the current. They are present as soon as the transformer is energized, regardless of whether a load current is flowing. Moving on to question 4. Name 2 types of iron losses. This is a straightforward recall question from our discussion. The 2 types of iron losses are eddy current losses and hysteresis losses. Again, 1 mark for each. Finally, question 5. Give an alternative name for hysteresis loss. The alternative name, found in our notes, is magnetic losses, because hysteresis is an inherent property of magnetic materials. Let's work through a full example problem to see how we apply what we've learned. The question states, in an electrotechnics test, you are presented with the following question. A transformer has a full load copper loss of 1500 watts and an iron loss of 1000 watts. The full load efficiency is 98%. You must show all calculations and round your answers to 3 decimal places. Step 1. Understand the given information. We are given the copper losses at full load, the iron losses, and the efficiency at full load. We need to calculate the total losses, the output power, and the input power. Step 2. Calculate the total losses. This is the easiest part. We simply add the copper losses and the iron losses. Remember, iron losses are constant, so they are the same at full load. The total losses are 1500 watts plus 1000 watts, which equals 2500 watts. Step 3. Calculate the output power. Here, we'll use the efficiency formula. The key is to rearrange it to solve for output power. The fundamental relationship is that efficiency equals output power over input power. We also know that input power is output power plus losses. We can substitute this into our efficiency equation. Now we can plug in our values and solve for P out. We have 0.98 equals P out divided by P out plus 2500. A bit of algebraic manipulation gives us an output power of 122,500 watts. Step 4. Calculate the input power. Now that we know the output power and the losses, we can use the input power equation. Input power is simply the sum of the output power and the total losses. Plugging in our values gives us 122,500 watts plus 2,500 watts, which is 125,000 watts. And that's how you can combine the concepts of transformer losses and efficiency to solve a practical problem. Always remember the 3 key formulas for efficiency, input power, and output power. Let's work through one more example that involves different loading conditions. The question is, a 50 kVA transformer has a full load copper loss of 500 watts and a core loss of 300 watts. Calculate the efficiency at full load and at 70% of full load. First, let's understand the terms. 50 kVA is the transformer's apparent power rating. The core loss is our iron loss. And 75% of full load means the transformer is delivering 75% of its rated power. Here's what we know. The apparent power rating is 50,000 VA. At full load, the copper loss is 500 W, and the iron loss is 300 W. We need to find the efficiency for 2 scenarios. Before we start, we need to know the power factor of the load, because P out is K equals phi. The problem doesn't give us one, so we'll assume the standard value for transformer efficiency calculations. We will assume a power factor of 0.8 lagging. Now let's calculate the efficiency at full load. We start with the full load output power, which is 50,000 times 0.8, giving us 40,000 watts. The total full load losses are the sum of the full load copper loss and the iron loss, which is 500 plus 300, or 800 watts. The efficiency is output power over output power plus losses, which is 40,000 over 40,800. This gives us 0.98039. As a percentage, the full load efficiency is 98.039%. Now let's calculate the efficiency at 70% of full load. The main difference here is how we treat the losses. First, the output power. It's 70% of the full load output power we calculated before. So 0.75 times 40,000 watts gives us an output power of 30,000 watts. Next, the losses. This is where our knowledge of variable and constant losses is critical. The iron loss, Pi, is a constant loss, so it remains 300 watts at 75% load. However, the copper loss is a variable loss and depends on the load current. Copper losses are proportional to the square of the load. So, the new copper loss is 0.75 squared times the full load copper loss. This gives us a new copper loss of 281.25 watts. Now we calculate the total losses at this load. It's the new copper loss plus the constant iron loss. 281.25 plus 300, which is 580.25 watts. Finally, we calculate the efficiency using our formula. Output power is 30,000 watts and total losses are 581.25 watts. The efficiency is 30,000 divided by 30,581.25, which is 0.9809. This is an efficiency of 98.09%. Notice something interesting. The efficiency at 75% load, 98.099%, is actually slightly higher than at full load, 98.039%. This shows that a transformer does not necessarily operate at its highest efficiency when running at its full capacity. The point of maximum efficiency occurs when the constant losses, iron losses, are equal to the variable losses, copper losses. Let's quickly review what we've learned today. We started by understanding why transformers are so efficient. It's their lack of moving parts that eliminates frictional and windage losses, leaving only electrical and magnetic losses to contend with. We then saw the classification of these losses into two main categories: variable losses, which depend on the load, and constant losses, which are load independent. And we saw that iron losses are subdivided into hysteresis and eddy current losses. We also discussed the nature of each loss: copper losses from winding resistance, stray losses from leakage flux, hysteresis loss from the core's magnetic memory, eddy current loss from induced currents in the core, and dielectric losses from insulation imperfections. And we learned key mitigation techniques, like laminating the core to reduce eddy currents. And finally, we put all of this into practice by solving two example problems, showing you how to calculate efficiency at different load conditions. This foundation is essential for your Electrotechnics N4 studies and for understanding real-world transformer operation. Thank you for watching Earthly Teachings. I hope this detailed tutorial has been helpful. Subscribe for more Electrotechnics N4 tutorials and revision lessons. See you next time. Thank you for watching Earthly Teachings. I hope this detailed tutorial has been helpful. Subscribe for more Electrotechnics N4 tutorials and revision lessons. See you next time.